Picture this. It's a summer afternoon. The thermometer reads 104 degrees Fahrenheit. You're standing outside, you're sweating, and you feel like you might pass out. Now picture this instead. The thermometer reads the same 104 degrees, but the air is thick with moisture. Your shirt is drenched, your sweat is not evaporating. Your body cannot cool itself down. And within hours, your organs begin to fail. Same temperature. Completely different outcome. The difference between those two scenarios is one of the most important scientific concepts you've never heard of. It's called wet bulb temperature, and scientists say it could define the limits of where humans can live on this planet within the next few decades. Today, we are going to break that down clearly, honestly, and with real numbers, because the heat crisis is not a distant warning anymore. It is already here, and it is going to get worse. To understand why wet bulb temperature matters so much, you first need to understand why two places at the same air temperature can feel completely different, and be completely different threats to your survival. Think of Phoenix, Arizona. It regularly hits 110 degrees Fahrenheit in summer. It is genuinely dangerous. People die, but the air is dry. And when you sweat in dry air, that's what evaporates. And evaporation pulls heat away from your body. That is your body's entire cooling system. Turn liquid sweat into vapor and carry the heat with it. Now think of Houston, Texas, or Mumbai, India, or any city on the Gulf Coast. Same extreme temperatures, but the air is already full of moisture. It is humid, and when the air around you is already saturated with water vapor, your sweat has nowhere to go. It sits on your skin, it drips off your body, but it does not evaporate. No evaporation, no cooling. Your core body temperature starts to rise. At a certain point, your body simply cannot keep up. Your internal temperature crosses 40, then 41 degrees Celsius. Your cells start to break down. Your kidneys fail. You go into cardiac arrest. This is the difference between dry heat and humid heat. And it is the reason scientists don't just measure temperature when they're assessing the danger of a heat event. They measure wet bulb temperature. Here's the simplest way to think about wet bulb temperature. Imagine a regular thermometer. Now wrap the tip in a wet cloth. The water on that cloth evaporates as air flows over it, just like sweat evaporating from your skin. The temperature that thermometer reads after the evaporative cooling effect is the wet bulb temperature. It combines two things, how hot the air is and how humid it is. When the air is dry, a lot of evaporation happens from the wet cloth, and the wet bulb reading is much lower than the actual air temperature. When the air is fully saturated with moisture, almost no evaporation happens, and the wet bulb temperature approaches the actual air temperature. A wet bulb temperature of 35 graus equal to about 95 degrees at 100% humidity, or 115 degrees at 50% humidity, was long considered the maximum a human could endure before they could no longer adequately regulate their body temperature, potentially causing heat stroke or death. For years, that 35 degree wet bulb threshold was the number climate scientists used in their models, the assumed human survival limit, the line you cannot cross and stay alive. But here is where the science gets alarming. That limit was based on theory and modeling, not real-world data from actual human subjects. When researchers at Penn State University finally tested it with real people, they found the actual danger threshold was significantly lower, about 30 degrees wet bulb, or 87 degrees at 100% humidity, even for young, healthy individuals. For older populations, the threshold is even lower. The real danger line arrives earlier than we thought, and for the elderly, the people most likely to die in a heat wave, updated survivability limits for older adults correspond to wet bulb temperatures as low as 21.9 degrees, which is up to 13 degrees Celsius lower than the old theoretical model. That is a massive difference. It means that large portions of the planet are already approaching dangerous conditions for older people, not just in future climate projections, but right now. There is a term scientists use that is worth understanding, the limit of compensability. It sounds technical, but the meaning is simple and terrifying. It is the point at which your body can no longer compensate for the heat around it. Your blood is pumping to your skin to release heat. Your sweat glands are working at maximum capacity. Your heart is racing. Everything your biology has to offer is already deployed, and it is not enough. Once you cross the limit of compensability, your core body temperature begins to rise. Not because you stop trying to cool down, but because the environment around you has made it physically impossible. The heat coming in is greater than the heat your body can expel. Wet bulb temperatures become life-threatening around 88 degrees. At 95 degrees wet bulb, the old theoretical survival limit, the maximum survivable exposure is around 6 hours. But the newer research suggests those 6 hours shrink considerably for anyone not young and healthy. For the elderly and the chronically ill, outdoor workers doing physical labor, or anyone in direct sunlight, the window is much shorter. And crucially, this assumes you are resting, not working, not walking, not doing anything except sitting still and trying to survive. For the hundreds of millions of people worldwide who work outdoors, farmers, construction workers, dock workers, heat beyond the compensability limit is not an abstract future threat. It is an increasingly real present danger. Now let us look at the map. Where are people already living close to these danger thresholds? And where will they be in 20 or 30 years if warming continues? With just 2 degrees Celsius of global warming, which could be reached as early as 2045 if greenhouse gas emissions are not reduced, vast areas of the planet could become regularly dangerous to live in. Some of the most populated regions, typically lower middle-income countries in the moist tropics and subtropics, would violate survivability thresholds well before 3 degrees C of warming. Further global warming extends the risk into drier regions, including North America and the Middle East. And let's make that concrete. The Indo-Gangetic Plain in northern India, one of the most densely populated agricultural regions on Earth. Hundreds of millions of farmers, already recording wet bulb temperatures in summer that approach dangerous levels. By mid-century, under moderate warming scenarios, this region could see conditions that make outdoor work during the day biologically impossible. The North China Plain, home to over 400 million people, similar dynamics, hot summers, high humidity from monsoon patterns, and a vast outdoor workforce. The Persian Gulf, already the hottest urban environment on Earth. Cities like Dubai and Abu Dhabi only function because of massive air conditioning infrastructure. Without it, they would be uninhabitable for much of the year already. And the U.S. Gulf Coast, Houston, New Orleans, Miami, already among the most humid cities in the country. Under high emission scenarios, excess hospitalizations from extreme heat in China alone could reach over 5 million annually by 2100. And these projections likely underestimate risk because they were based on the old, higher survival threshold. The comparison between regions reveals a brutal pattern. The places that are hottest and most humid are also, almost universally, the places with the least capacity to adapt, poorer infrastructure, less reliable power grids, lower rates of air conditioning ownership, older and more vulnerable populations. This brings us to the solution that everyone reaches for first, air conditioning. And air conditioning does save lives, there is no question about that. Access to air conditioning already saves tens of thousands of lives a year, a figure that is growing. In the United States, 9 out of 10 homes are equipped with air conditioning. Globally, there are now roughly 2 billion air conditioning units installed, with that number expected to triple by 2050. But here is the paradox that makes this problem so much harder to solve. Air conditioning works by pulling heat out of a room and dumping it outside. When millions of units do this simultaneously in a city, they raise the outdoor temperature. Air conditioning units in urban areas have been found to raise street temperature by as much as 1 degree Celsius. So air conditioning makes the city hotter, which makes people need more air conditioning, which makes the city even hotter. And it gets worse. If unmitigated, air conditioning alone will be responsible for a 1.5 billion ton annual rise in CO2 emissions by 2030, more than 3 times the emissions of the UK or Brazil. By 2050, cooling could account for 10% of global greenhouse gas emissions. So the tool we are using to survive rising temperatures is contributing directly to the warming that creates those temperatures. We are cooling ourselves into a hotter future. And perhaps the cruelest dimension of all, air conditioning is unavailable to households with no electricity and remains unaffordable for many low-income households. The lack of green spaces and proximity to industrial operations make lower-income districts hotter than wealthier neighborhoods, pushing them further toward energy poverty. The people who most need cooling are the least able to access it. The people who can access it are accelerating the warming that the most vulnerable cannot escape. Extreme heat kills more people than any other climate disaster on the planet, including hurricanes, floods, and wildfires. In India, cities inhabited for centuries are now recording highs of 123 degrees. Between 2002 and 2021, heat-related deaths of people 65 and older increased by 61%, reaching 345,000 in 2019. That number is going up, not down. There's one more layer to the air conditioning paradox that does not get enough attention. What happens to the power grid when everyone turns their AC on at the same time? During New York City's 2019 heat wave, on a Sunday in July when the heat index hit 113 degrees, neighborhoods in Brooklyn and Queens lost electricity. Because the system handling record-breaking load to power room air conditioners caused several sections of the southeast Brooklyn grid to fail. That is the feedback loop in real life. Heat drives demand for cooling. Cooling overloads the grid. The grid fails. People are left without cooling in the middle of a lethal heat event. This is not a problem unique to New York. Power grids across the American South, across South Asia, and across the Middle East face the same pressure every summer. And as peak heat events become more frequent and more intense, the grid failures will become more frequent too. So where does this leave us? The answer is not to abandon air conditioning. People will die without it, but the answer is also not to simply build more AC units running on fossil fuel power. That leads us further into the feedback loop. The real solutions work on two levels simultaneously. The first is energy. Climate-friendly and more energy-efficient refrigerants can replace harmful synthetic gases. With the Kigali Amendment, signatories have committed to cutting the use of hydrofluorocarbons by more than 80% over 30 years. And it is estimated this alone could prevent a 0.5 degree increase in global temperatures. But the deeper solution is transitioning the entire power grid to clean energy. If the billions of air conditioning units that will exist by 2050 are powered by solar and wind rather than coal and gas, the cooling paradox dissolves. You can cool homes without warming the planet. The second level is urban design. Green roofs and urban vegetation have been found to reduce not only the need for cooling within buildings, but also to cut the average land surface temperature across project zones by nearly a full degree Celsius. White roofs, which reflect sunlight, can reduce indoor temperatures by as much as 30 degrees Celsius, greatly reducing cooling demand. Trees, green spaces, reflective surfaces, better insulated buildings, natural ventilation. These are not futuristic fantasies. They are proven technologies being deployed right now in cities across Europe, Asia, and North America. They work. They are cheaper than air conditioning. And they help everyone, including the people who cannot afford an electricity bill. So let's return to the original question. When will extreme heat become unlivable? The honest answer is, for some people, in some places, it already has. Under 1.5 degree of warming, 52% of people born in 2020 are expected to face unprecedented lifetime exposure to extreme heat. Under 3.5 degrees of warming, that figure rises to 92%. 92%. That means 9 out of 10 children alive today will, in their lifetimes, experience heat conditions that have never existed in recorded human history. This is not a problem for future generations. It is a problem being handed to the children who are alive right now. The science is settled. The wet bulb threshold is lower than we thought. The warming is faster than we planned for. The populations most at risk are the most vulnerable and the least responsible for the emissions driving the crisis. But the solutions exist. Clean energy, better buildings, smarter cities, more trees, cooler roofs. These are not complicated technologies. They are political choices. Limiting warming to under 2 degrees nearly eliminates the risk of mass uncompensable heat stress. Nearly eliminates. That is the difference between a manageable future and an unlivable one. The human body has physical limits. The planet's atmosphere is approaching them faster than we admitted, and the window to change course is narrowing every year. The question is not whether we have the tools to survive what is coming. The question is whether we have the will to use them.